MSTP, or Multiple Spanning Tree Protocol. This is the last version in the STP family, and like the others, it prevents loops in a layer 2 network. But what is MSTP? What benefits does it bring, and how does it work? These are all questions plus more that we'll be going through in this detailed video. Hey everybody, and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And on this video, what I'm going through is MSTP, or Multiple Spanning Tree Protocol. And as I said in the intro video, this is really the last edition. It's the last part of the STP family. There's Spanning Tree Protocol, or STP, and then there's Rapid Spanning Tree Protocol, or RSTP. And when you look at STP and RSTP, what is the one thing that they both have in common? The one thing that they've got in common, minus they prevent layer 2 loops, of course, is that they are not VLAN aware. They simply do not know or care about the VLANs in the network. Whether you have 1 VLAN, 5 VLANs, 10 VLANs, 100 VLANs, it does not matter. That architecture, that topology that is built is going to be the same for all VLANs in that layer 2 network. Whereas MSTP, Multiple Spanning Tree Protocol, there's the key word, multiple, is it takes VLANs into account. It is VLAN aware, and thus you can have multiple instances, key word there, multiple instances of spanning tree in that layer 2 network for a group of VLANs, or maybe for every single VLAN, depending on how you want to do it. And in this video, as I said, we're going to start off with what are the benefits to MSTP? How is it different to PVST or PVST plus if you're coming from the Cisco world, or the standard being VSTP, VLAN Spanning Tree Protocol? How is MSTP different? What benefits does it bring? And then we're going to build on top of that and go into what are the key components that you need to know for MSTP, such as what is the IST, what is the CST, what is the CIST, new acronyms I know, and even what is this master port that you have in the MSTP world that you do not have in STP, RSTP, or even VSTP, or any of those combinations. So stay tuned, this is going to be a detailed video, and for now let's just get straight into the theory and let's go from there. Okay, so let's start with this basic question. Why do we need MSTP? We know it stands for Multiple Spanning Tree Protocol, but why do we actually need it in the first place? Well, when you compare it to VSTP, which is the equivalent, as I said, to Cisco's PVST or PVST plus, and it stands for VLAN Spanning Tree Protocol, this similarity between VSTP and MSTP is that they are both VLAN aware, just like PVST and PVST plus. So you can configure your layer to have a different spanning tree protocol tree for every single VLAN, because that's what VSTP or PVST, PVST plus actually do. And what this allows, is a sense of load balancing. If you look at this very basic network, we've got switch 3, which is that access layer switch, and then we've got switch 1, switch 2 are those distribution layer switches. And with VSTP, with PVST, with PVST plus, what you can do, because you can have a different tree for every single VLAN, is you can essentially have a different root bridge for every different VLAN, or for a group of VLANs. And so if we take this as a good example, let's just say you've got 20 VLANs in your enterprise network. And what you want to do is you want to distribute that load balancing between switch 1 and switch 2. So what you could say is, okay, switch 1, you're going to be that root bridge for VLANs 1 to 10. Whereas switch 2, you are going to be that root bridge for those VLANs 11 to 20. And this obviously has some benefits to it, because we're load balancing that traffic. So all the VLANs 1 to 10 will go to switch 1, and presumably that link between switch 3 and switch 2, as you can actually see, it's an alternate port. It's blocking, it's discarding any traffic. Whereas for the VLANs 11 to 20, switch 2 is that root bridge, but that interface between switch 3 and switch 1, that is alternate, that is discarding any traffic. So yeah, that's a benefit. We're using all available links and we're load balancing across the network. So with that in mind, what are then the disadvantages to this? Well, the disadvantages are actually very straightforward. And that is, first of all, the amount of bridge protocol data units that every device is going to send out. So we've got the root bridge here for VLANs 1 to 10, and we've got the root bridge switch 2 for VLANs 11 to 20. Now, if we look at the BPDU for the hello timer, if you know the theory, the hello message, that hello BPDU is being sent out every 2 seconds. So that means the root bridge is sending out a hello over here and a hello down there, and at the same time the root bridge switch 2 is sending a hello over here and a hello down there, and it's doing so for every single VLAN. So for VLANs 1, 2, 3, 4, 5, I'm not going to do it all the way, but you get the idea. All the way up to 20, it's sending a BPDU out every 2 seconds, as I said, for every single VLAN. And as such, that's quite intensive, isn't it? That's intensive both in terms of bandwidth, because we're using up a hell of a lot of bandwidth. Even though they're small BPDUs, it all adds up. You're using bandwidth on those interfaces. You're using bandwidth on those links that could actually be used to pass data traffic. But also you've got to look at the CPU, the resources on the switches themselves to actually receive, process and understand every single one of those BPDUs per VLAN. Typically, let's be honest, for access layer switches, for this switch here, typically users will go lower spec to keep the cost down. It's just the reality. We do it ourselves for every walk of life, whether it be your mobile phone, tablet. Typically we like to keep the cost down. It's perfectly understandable. But when you've got lower spec switches, potentially, are they going to be able to receive, buffer and process those BPDUs for every VLAN every 2 seconds? I'd like to think so. Regardless of vendor, I'd like to think so. But obviously there's going to be a limit, and the lower spec just basically means that limit is hit a lot sooner than higher spec switches. So these are really the downfalls when it comes to VSTP or even PVST, PVST+, is that they are essentially resource intensive, whether it be on the interface, the bandwidth on the interface, or on the resources on the device themselves. They require quite a lot of resources, and every vendor, whether you look at Juniper, Cisco, Arista, they kind of do limit the amount of PVST or VSTP instances that you should run. Just saying, it is resource intensive. This is the problem. This is why MSTP essentially came about. But how is MSTP different? Well, what it does is it groups, keyword there, it groups into an instance, into a multiple spanning tree instance, a group of VLANs. So if you look at it from VLANs 1 to 10, they are aligned to MSTI, multiple spanning tree instance 1. And if you look at it from VLANs 11 to 20, they are configured into MSTI 2. And this is different because what you have is you have one instance which is known as the CIST. I'll come on to this in more detail obviously in a few minutes time, but this is by default created whenever you configure MSTP. It's automatically created. Is that this CIST, which is default, configured by default, is it will send out those BPDUs, and the benefit of that is instead of having a BPDU for every single VLAN, now you have only one instance sending out that BPDU for all VLANs. So you don't have 20 times BPD used for these 20 VLANs here. Now we've only got this one default instance, this one IST, sending out those BPDUs, yes, every 2 seconds, that doesn't change, to all devices. And that is a lot less resource intensive, both in the sense of bandwidth and on the devices themselves. And if we use the example over here, as I said, there's 2 instances, didn't I? There's MSTI1 and there's MSTI2. So we still got the root bridge over here for switch 1 for these VLANs here. And we've still got the root bridge on switch 2 for these VLANs here, VLANs 11 to 20. But just to home it in again, those root bridges, they're only sending out that BPDU for that one instance, and that is for all VLANs, for all instances which contains those groups of VLANs every 2 seconds. One instance doing it all instead of every VLAN having a BPDU sent out. So yeah, that is why MSTP came about. So as I said, an MSTI, or multiple spanning tree instance, is really just an alignment, it's a configuration. It's a mapping of specific VLANs to a specific instance. And there is, as I said, there is this default MSTI, this default multiple spanning tree instance, and that is called the IST, or the internal spanning tree. So whenever you create, you configure, you commit that command, that configuration to have MSTP in your network, by default you are going to have this IST, this IST0 or MSTI0. It's all the same thing, to be honest. Just know that the default MSTI0 is called the IST, the internal spanning tree. And you cannot disable this, and this is needed because it is sending a BPDU, as I just said, for all the VLANs that are both grouped, aligned, configured to be in MSTI, and it's all the non-active VLANs. And it's also sending BPDUs for all the other instances as well that have all those active VLANs aligned, configured, and mapped to them. And what you can also do, and this is really the cool thing with MSTP, is that you can have a primary and a backup, a primary and a secondary. So in this case, where switch 1 is the root bridge for VLANs 1 to 10, you can configure switch 2 to be the secondary, the backup root bridge for VLANs 1 to 10. So if switch 1 fails, then switch 3 just knows to divert traffic over from one link over to the other, and obviously change those port modes, those port types. But what you also have to understand is that multiple spanning tree has this concept of regions. What is a region? It is simply a group of switches that have got the same configuration, i.e. the same configuration of instances. So whether you have the default instance, IST, or the MSTI0, or you've got 3 instances, as I'm showing here, if all switches in that network domain, in that layer 2 network, have the same configuration, then they're going to be recognized as being in the same region. Any switches that do not have that same configuration are going to be recognized as being in different regions. And this is a really cool thing, and we're going to build on this. But what are those configurations? Those configurations that have to match from switch to be in the same region, first off is the configuration name. Now this is optional, you don't have to configure this, but I advise to configure it because it's a nice easy way to identify which instance is which. So whether it be MSTI 1 or 100, it's got to be a numerical value. It's just good practice to name it. Yes, it's optional, but that's one of the attributes that has to match from switch to switch for it to be in the same region. The other optional command, the other optional configuration, I should say, that has to match for all switches to be in the same region is the revision number. Now, honestly, this does not serve any purpose, this revision number. It has no significant use whatsoever, and it doesn't even automatically update itself. The default is 0. It doesn't even automatically update itself when you push a new configuration change. So it is completely optional at the end of the day. But if you make a configuration change, whatever that may be, you might want to change that revision number from 0 to 1, from 1 to 2, etc. But again, that value has to match on all switches, as well as the name, the configuration name, for all switches to be identified in that same region. And then there is this MST instance to VLAN mapping table. What is this? Well, let's look at it from switch 1. So let's say this is SW1 over here, and over here we've got SW2. They are going to have a VLAN to table mapping. So let's say we've got VLANs 1 to 10, just keeping it simple. And we've got VLANs 1 to 10 on SW2 as well. What they will do is they will derive a hash calculation, just a hash value, and they'll send it to each other. And if these two values match, then they know that they have that same VLAN mapping, that same VLAN to mapping table. If, for example, this was on switch W2 here, it had VLANs 1 to 20 and SW1 still had VLANs 1 to 10, switch W2 would send out a value, a hash algorithm, and I'm going to keep it simple, of Y, but switch W1 would send out a hash algorithm, a hash calculation, sorry, of X. Obviously, they're not going to match, and from that, they are not going to be in the same region. But those are the three, and there's actually four, but the fourth one is some kind of configuration identifier, but it's never used. You can't configure it. It's always set to 0, and thus I'm not showing it. But these are the three configurations that need to match. Yes, 2 of them are optional, but they need to match for all switches, in this case, switch 1, switch 2, and switch 3, to be identified as being in the same region. Again, if they do not match, that switch, whatever the switch is not going to be in the same region, because the hash algorithm will be off, or the revision number won't be the same, or maybe the configuration name won't be the same. It has to match from switch to switch for the switches to be in the same MSTP region. And here's actually a packet capture. Honestly, this isn't one that I done. I just grabbed it off good old Google, to be honest. But looking at the packet capture, you could see all the bridge protocol data unit information. So you could see it's MSTP. We can see it's running rapid MSTP. As I said, MSTP is built on RSTP for the rapid convergence. But if you look down here, note here are those 4, or really the 3 attributes that I just mentioned. This is that one that you can't configure, you can't change. It's always set to 0, so don't worry about that. But here you've got the configuration name. Note it's not entered because it is optional. Here's the configuration revision number. That is 0 by default, and here is that hash algorithm. I keep calling it a hash algorithm. It's not. It's a hash calculation. But here's that hash calculation again. Those 3 have to match. Pretty interesting. So as I've said quite a few times, those attributes, those configurations, those values have to match for each one of those switches to be in the same region. If you have a switch that doesn't have the same values, whether it be the same configuration name, the same revision number, or the same instance to VLAN mapping, so MSTI1 having VLANs 1 to 10, and MSTI2 having VLANs 11 to 20, so say it's configured differently just for that one attribute, then it's going to be recognized as being in a different region. And what you have at this point is what's known as a regions boundary. We're going to come onto this in quite a few minutes time, but just know this is a boundary between one region and another region, and you're going to have something called a boundary port. Come on to that in a few minutes time. But what is really cool about this is that from that outside switch perspective, from that switch that isn't in the same region, it will identify, it will see switch 1, switch 2 and switch 3 as one logical switch, because they're in the same region. They have the same instance to VLAN mapping. They have the same VLANs mapped to the same instance. They have the same hash calculation. They have the same revision number. They've got the same configuration name. And thus it sees it as one logical switch. And just so you know, between this one region and this other region, you're going to have something called a CIST, or common spanning tree. Coming on to this in a few minutes time. But I think that's really cool, really interesting, because even though you could have 2 switches, 3 switches, 10 switches, from an outside switch's perspective, and that outside switch could be running STP or RSTP, it doesn't even have to be running MSTP. It sees all of those switches as one logical switch. And that's why you've got a boundary and a boundary port, because it's really saying, yep, this is a boundary from one region to another region, from a non-MSTP speaking switch, potentially, to this one logical switch. That really, those physical switches, 3 in this case, they all actually are part of. But absolutely, always remember, within any region for MSTP, you are going to have that default IST, the internal spanning tree. That is MSTI 0. All the non-active VLANs will be automatically aligned, mapped to that. What do I mean by non-active VLANs? Well, if I go back, you can actually see VLANs 1 to 10 are aligned to instance 1, and VLANs 11 to 20 are aligned to instance 2. But what about the other VLANs from VLAN ID 21 plus? They will automatically go to MSTI 0 because they're non-active. They've not been actively aligned, mapped, configured to a specific instance. But 100%, please check documentation on the vendor's limitation on the amount of regions that a switch can support. It will vary, so please check that out. So at this point you might be asking yourself, why do you need a multi-region? Surely it's quicker and easier if all switches were in the same region. Well, yeah, of course. Obviously it would be far less complex if all switches were in the same region, but the reality is that's just not going to actually happen. And the reason why I say that is because if you look at this, if you look at region 1 here, where you've got switch 1, switch 2, switch 3, there's 3 instances. There's MSTI 0, which is the internal spanning tree. I really want to hammer that point home. That the MSTI 0, that default instance, is the IST. The IST is sending out the BPDUs for every single instance for MSTI 0, for MSTI 1, and for MSTI 2 to calculate that loop 3 topology every 2 seconds. But if we look at these instances, you can actually see the non-active, being the word, the non-active VLANs for the default IST, 21 to 4096. If you look at MSTI 1, there's VLANs 1 to 10, and for MSTI 2, there's VLANs 11 to 20, and thus these here are active. VLANs 1 to 10 and 11 to 20 are active, but from 21 up to 4096, they're not active, they're not being used. But if you look at region 2, it's slightly different. If you look at the MSTI 0, i.e. the IST, we've got 11 to 20, and then 31 to 4096. Immediately you could see that's different to region 1's IST. The reason being is because for the instance 1 over here, it's the same 1 to 10. That's the same as over here in region 1. But if you look at region 2's instance 2, it's VLANs 21 to 30. Instance 2 in region 1 has VLANs 11 to 20. What does that mean? That means that the hash calculation, which is derived from that VLAN to instance mapping, it's not going to be the same from the hash algorithm that's in region 1. The 2 hash calculations between region 1 and region 2 are going to be different. And this comes back to the reality that in an enterprise network, you are going to have some VLANs which are needed in one area of the network, but are not needed, not relevant in another part of the network. And when you have MSTP running, and you've got this concept of instances, and instances going to a region, if one of those instances don't have the same VLAN to instance mapping, that's going to offset that hash calculation. And if the configuration name and the revision number is additionally different, then they're just automatically identified as being in different regions. And thus, this is how you end up with a multi-region MST network. And what I've done is I've actually just put in the port rows for region 1 and for region 2. Now I'm keeping this simple at this point. I'm only doing this for the IST. I'm only doing this for both regions for MSTI 0. If I was to do this for MSTI 1 and MSTI 2 in both region 1 and region 2, this is going to get complicated. It's going to get way too messy. So I'm keeping it simple. Just note that these port rows are for the IST, the internal spanning tree, which is the default instance. It is the default MSTI 0. These port modes are just for that MSTI 0. But what you could see in region 1 is that switch 1 has become that root bridge because it has the lowest priority, and thus its interfaces are in the designated port. We've got root port here on switch 2, root port here on switch 3, and the interface here on switch 2 is alternate, is discarding traffic. Again, this is only for MSTI 0, i.e. the IST. I keep saying that, but I really want to get that point through. And if you look over at region 2, which one is the root bridge? It is, of course, switch 6. It has the lowest you can get the priority of 0, and thus its interfaces are designated port. We've got root port here on switch 4, root port here on switch 5, and here between switch 4 and switch 5, this interface right here is discarding any traffic. Again, just for MSTI 0, not 1 or 2. It'll get too complicated. But then when you've got a multi-region MST network, you've got region 1 and region 2, how are you going to connect the two together? Well, in MST, what you have is this new acronym called CST, or Common Spanning Tree. So the Common Spanning Tree, the CST, it builds, guess what, that tree between different regions. And as you can see, they're in different regions because the hash that was calculated in region 1, and as I just went through, it's going to be different to the hash that was calculated because of that VLAN to instance mapping in region 2. So these are different regions. And now you need CST to build that inter-region, to allow that inter-region traffic to actually take place. But absolutely 100% remember that region 1, from region 2's perspective, it's just going to appear as one logical switch. And likewise for region 2, from region 1's perspective, it is also going to appear as one logical switch. And then between here, you have that common spanning tree actually running. And as you can see here, there's actually two interfaces. So if you think of it, if this was one switch and another switch over here, and you've got two interfaces, what is the role of spanning tree at the end of the day? Is to prevent a loop, is to ensure there is a loop-free topology. And that is why you've got designated ports here, we've got root ports here, and then you've got alternate port here, which is going to block that loop. So yes, a region is a lot more than a single, well, it can be a single switch actually, but it's a single logical switch from an outsider's perspective. Inside that region, you could have multiple or several or many switches actually in that same region. But from the outside's perspective, it's a single logical switch. And to ensure that loop-free topology and which ports are designated and which ports are root port and alternate discarding, that's the job of CST. And we're going to build on this in more detail very, very soon. But in region 2 will actually become the root for this network, because don't forget, coming back to it, each one of these regions is viewed as a logical switch. And just with any switched network, you're going to have a root bridge in one network, and then you're going to have non-root bridges as well. So it's no different, it's just from a much larger scale. But we're going to come into how region 2 became the root bridge in just a few minutes time. But what there is in the MSTP world as well is this concept of boundary ports. Now the boundary ports are actually connected to region 1. Why are they not connected to region 2? The sole reason being is because, and again we're going to go through this, region 2 is that route. It's the route bridge for this network. And when you have a route bridge, all of those interfaces on that route bridge will be a designated port. On those non-route bridges, in this case, this logical switch here, which is region 1, you're going to have one route port, obviously, and then you're going to have an alternate port to discard the traffic to prevent a loop-free topology. And it's these interfaces here that are the boundary ports, because they're the boundary from region 1 to region 2. Region 2 has the designated ports connected to itself, and thus it can't be a boundary because it is the route. Region 1 is not the route for this network, and therefore these are the boundary ports. So basically, just know and understand the boundary ports are on the non-route bridge, facing that route bridge from region 1 to region 2. Region 1's interfaces connected to region 2 are the boundary interfaces. And here comes another new, and I promise you this is the last acronym, the CIST, which stands for Common and Internal Spanning Tree. Now hopefully the name gives it away. What is CIST? It is a combination. It's the aggregation of the IST in region 1, the IST in region 2, and the CST coming together. So if we do that here, this then becomes the CIST, the Common and Internal Spanning Tree. And just to recap, the internal spanning tree is for inside a region, that is MSTI 0, sending out those PBDUs to calculate a loop-free topology for all instances, for instance 0, for instance 1, and for instance 2, and the same in region 2. And then we've got the common spanning tree, which ensures that loop-free topology between region 1 and between region 2. And it all comes together to bring common and internal spanning tree. But coming back to that last slide, to one of the last points, is do you need a route bridge for a CIST? Do you need a route bridge for a common and internal spanning tree? The answer is yes, you absolutely need a route bridge. Spanning tree, whether it be STP, RSTP, MSTP, VSTP, PVST, or even PVST plus, or anything else that I don't know about, it needs a bridge. It needs a route bridge. And as always, that route bridge is elected. It's elected by the lowest bridge identifier. Firstly, the lowest priority, and if there's a tie in the priority, it then goes into MAC addresses and so on and so forth. But coming back to here, remember on the last slide, I said that region 2 was the route bridge, because all of this is recognized as one logical switch, isn't it? But more specifically, what switch inside of region 2 is that route bridge? Well, switch 4 has this priority of 8,192, switch 5 has this priority of 32,000, and switch 6 has this priority of 0. That is higher than the priority of switch 3 in region 1, of switch 2 in region 1, and switch 1 in region 1. And therefore, that is why switch 6 has become that route bridge. But again, it's recognized as one logical switch, and thus region 2 has become that route bridge between region 1 and region 2, because they're just seen as, from an outsider's perspective, as one big giant switch at the end of the day. But when you look at it from a switch by switch perspective inside of the region, inside region 2, switch 6 is that route bridge because it has the best or lowest priority for all the other switches, even in the switches in region 1. And I've just talked on these points here, so I'm not going to go through that. But there is an official MST word for SW6. It is the regional route. That means it is the route bridge for region 2 and the CIST route. Remember I said the CIST is the combination of the IST for all regions and for the common spanning tree. And because it has that best or lowest priority, it is the route bridge for region 2 and for region 1. But if you look at it from region 1's perspective, it too will have a regional route. Which will that be? That will be switch 1, because this has a priority of 4096. So even though it's not a CIST, because this priority here is higher than the switch 6's priority over here of 0, it still has the best priority inside of region 1, and thus this here has become the route bridge. But just know at the end of the day, the CIST is the combination of the internal spanning tree in each region and the CST. I know I'm getting confused on the acronyms themselves, a bit of tongue twisters. And in each region, you're going to have a regional route that is going to be elected, decided by the best or lowest priority. We could say switch 1 is the regional route for region 1, and switch 6 is the regional route for region 2. But the CIST is that multi-region route bridge, because, again coming back to it, region 1 and region 2 are recognized as two different regions, as two different virtual logical switches. We've got region 1 and region 2. And because in here there's SW6 with that lowest priority, this then becomes that route bridge, or as it's officially called, the CIST route. But why on earth make it so complicated? It's just the protocol at the end of the day, but hopefully this helps. I've said it a few times. Just know that every switch, every region, from an outside's perspective, is seen as one giant logical switch. So even though in region 1 there was 3 switches connected together and the same in region 2 connected together, it's seen as one logical switch. And just like logical switches, they have to be connected to and from each other. That's where the CST comes into it, and the CIST combines all of that together. And because we've got logical switches speaking with each other, you need one as the route bridge. The other will not be a route bridge, but from an MST perspective, you're still in here going to have, in region 1 you're going to have a regional route, which was switch 1, and in region 2 you're going to have a regional route as well, which was switch 6. But switch 6 was also that CIST route for this combined common and internal spanning tree. Okay, so let's now build on the CIST regional route, the election, and how as well these ports are actually elected to be in the mode that they actually are. But first let's look at region 2. Specifically, let's look at the port rows. So we know that switch 6 is the regional route for regional 2, it's the route bridge, and it's also the route bridge for the common and internal spanning tree, i.e. region 1 over the CST and region 2. We know that. And as always with STP and RSTP, it's the same with MSTP. What switch 4 and switch 5 are doing is they're basing their decision on which port's going to be route and which is going to be alternate, which is going to be a designated port, based on the best or lowest cost to get back to that regional route, which is switch 6. And now what I want you to do is just look at the interfaces in region 1. And what I want you to do is just do a mental screen snapshot, as it were. So we've got designated port, route port, designated port, alternate route port. And as we've said, switch 1 is that route bridge. It's the regional route bridge. But this was without the regions being connected over or through common spanning tree, i.e. switch 1 was that route bridge without CST in the mix, without regions. When you've got regions, when region 1 is connected to another region, region 2, it changes. Now look at this. Look at the interfaces now in region 1 in terms of those port rows. So we've got the alternate port, the discarding port here, whereas before it was over here. Look at switch 3. It's now got 2 designated ports, which kind of says that switch 3 is now that regional route. It is that route bridge for region 1, that regional route. And if you look at switch 1, it's now got a route port right here. You can't have a route port on a route bridge, even though it's got a lower priority of 4096 compared to switch 3. It's now got a route port. What's happened here? What's happened here is that basically with CIST, with this guy in the middle here, this common spanning tree, we've connected region 1 and region 2 together. And if you look at switch 1, it doesn't have a connection over to region 2, does it? So without that connection, it can't have a boundary interface. And thus, it just simply can't pass traffic from region 1 to region 2. Yes, we know that SW6 is the regional route for region 2 and the CIST route for both regions 1 and 2. But we need a switch with the best or lowest priority to get from region 1 over to region 2. And because switch 3 has this priority of 8192 versus switch 2's priority of 16,000, that is why switch 3 has become the regional route for region 1. So you can see there how quickly things change in the MST world when you start connecting networks or regions together. Before, switch 1 was that route bridge, but as soon as we connected region 1 to region 2 over a common spanning tree, switch 1 wasn't that route bridge anymore. No, it's suddenly switch 3 was that regional route bridge for region 1. But again, the CIST route for both regions is switch 6. So just know in summary that when you've got regions connected together using CIST, and again this is only for MSTI 0 for the default instance, that you're going to have some port changes because we need boundary interfaces to get from one region to another region. And if that route bridge, switch 1, doesn't have, in this case, switch 1 doesn't have any boundary interfaces to get from one region back to the CIST route, then things have got to change. We've got to have one of those other switches become the regional route which has that boundary interface. So let's go through a little bit more detail into not the CIST regional route. We know that that's going to be SW6 and SW3, and that the CIST route is SW6 as well. But what I want to go through is how is the port rows here actually determined in this common spanning tree in this CIST. Well, as always with anything STP related, lowest the cost, the better it actually is. So what we have between region 1 and region 2 are what's called the external paths. So external being external to region 1 and region 2. And obviously over these interfaces themselves, whether they be giggy or fast Ethernet or slower or even faster, they're going to have particular costs, aren't they? And as I was just saying, in the STP world, lower the cost, always the better. And with these CIST interfaces, these external paths, the interface which has been elected as alternate or discarding between region 1 to region 2 is this interface actually here. It doesn't really matter about the interface number. I just wanted to keep the display, the illustration as simple as possible. But you can actually see that this interface here has been elected as the root port. Yes, they're both boundary interfaces, but this is the root port because it had a lower cost. And what you also have to take into account when it comes to these external paths is it's the external route path cost to get from region 1 over to region 2. So it's SW2's cost to get over to SW4, and it's SW3's cost to get over to SW6, which just happens to be the CIST route. So it's the cost of both of these which are actually compared, and again, lower the cost, the better it is. but it does not take into account, it does not include in its calculation the internal cost inside of that region. So if we look at it from SW2's perspective, to get over here, it's only looking at the cost on this interface here. It's not taking into account the cost of the interfaces to go from SW4 through SW5 to SW6 and even from SW4 down to SW6. It's not taking those into account. It's not taking into account these internal costs. It's the external costs only, i.e. the ones going over those boundary interfaces between regions. And we've already gone through this because SW1 here did not have any boundary ports. That is why we saw the route interfaces on those bridges actually changing and SW3 becoming that regional bridge for region 1. But both SW2 and SW3, they've got these boundary interfaces, haven't they? And again, they're taking into account the external cost to get from region 1 to region 2. What if there's a tie between the two interfaces here? Well, in such a case, lowest bridge identifier is actually used. So if there's a cost, if this was a GIGI interface here and this is a GIGI interface here, that would be something like 20,000 using the long cost that you get from the RSTP world. But then it takes into account what's the lowest bridge identifier, the priority. SW4 has got 8,192. SW6 has got a priority of 0, and that is why this interface here is a root port and this interface here is basically discarding. Because again, remember, logically these regions are seen as two great big giant switches with two links going over them. One needs to be discarding and one actually needs to be forwarding that traffic. But what about the other MSTIs, the multiple spanning tree instances? Everything I've shown so far has been from MSTI 0's perspective, hasn't it, for both region 1 and region 2, i.e. MSTI 0 being the internal spanning tree, being the default instance that's automatically created whenever you enable MSTP. But as you can see, for both regions, there's also MSTI 1, MSTI 2, MSTI 1 and MSTI 2. So everything we've done so far has been about MSTI 0, but what about these other instances, which you're pretty much going to have when you have MSTP configured? Well, let's first look at it from region 1's perspective. What instances and VLANs do we have? Well, we've not taken MSTI 0 into account. We've talked about that, but let's look at instance 1. VLANs 1 to 10. Do we have VLANs 1 to 10 in region 2? We do have VLANs 1 to 10 in region 2. We have VLANs under MSTI 2, VLANs 11 to 20 in region 1. Do we have VLANs 11 to 20 in region 2? The answer is we do not. So therefore, VLANs 11 to 20, they are isolated to region 1. So if we look at it from here, do we want 11 to 20, those VLANs and all that traffic to be sent from region 1 to region 2? No, we do not. They do not need to go over that common spanning tree protocol. They do not need to pass to region 2. And let's now look at it from region 2. Yes, we've got VLANs 1 to 10 over here, but we've also got VLANs 21 to 30. Do we have 21 to 30 in region 1? The answer is we do not. So again, VLANs 21 to 30, they are isolated to region 2. We do not need traffic to pass over that CIST for all traffic associated to VLAN tags 21 to 30. But the common denominator, the common VLANs which are in both regions are VLANs 1 to 10 here. So what we do need to go over the CIST, over the common spanning tree, are the VLANs, the traffic assigned to VLANs 1 to 10. So yeah, VLANs 1 to 10, they are in both regions. They're in both region 1 and in region 2. And so therefore, we need that traffic, as I was just saying, to pass over that common spanning tree, that CS2, from region 1 to region 2, and from region 2 back to region 1. And building on these points, yeah, the traffic has to be passed over the CST. I've said that a few times. Remember that each of this is a single broadcast domain. And switch 1 is the root bridge for MSTI 1 in region 1. So here now for switch 1, you can actually see this is a designated port, this is a designated port, root port, designated port. So no longer is switch 3 the root bridge, because that was for MSTI 0, isn't it? We're actually talking about MSTI 1. And the problem there is, because of that, is that every switch can only have one root port. And you might be thinking, well, hang on, Dave, when we're talking about MSTI 0, this here was a root port and this here was a root port. But again, that was for MSTI 0. Again, remember, each one of these is a logical switch. Each one of these regions is a logical switch, which just happens to have these two connections going over it. And right here is that root port. Region 2, this switch here cannot see inside this region here and see all these little switches that are connected together. No, it can't. But what we're saying here is that switch 3 cannot use this root port here again for another instance. And because of that, there's now a new term called master port. So now, instead of using this interface here as a root port for the CST, for all other instances that is not the MSTI 0, the IST, it's going to be a master port. And this basically allows traffic to pass for all other different instances between the different regions. So for MSTI 1 and for MSTI 2, it allows traffic to pass over this interface here for all those instances. And what the master port basically does is it allows the traffic for that VLANs, for VLANs 1 to 10, to pass from one region over to another region and obviously back again. And what it also allows to happen is for all instances, for all MSTIs, for that traffic to go over that same instance. So for MSTI 1, for MSTI 2, for MSTI 3, 4, etc., they can all use this master port. So if we again look at it from the logical perspective, where each region sees one big giant switch that they're connecting to, we can actually now use the master port here for all instances in this logical switch here, and from region 2 for all instances here 1, 2 and 3 to use the designated ports actually connected to it. So yeah, master port basically allows traffic to pass between regions for all the instances that is not the IST, i.e. the default instance, the MSTI 0. So let's finish off by quickly reviewing what we've gone through. First and foremost, the IST, the internal spanning tree, or MSTI 0, that multiple spanning tree instance 0. They're exactly the same thing. Automatically created for you, it's just there by default. It's the default instance and it's for all non-active VLANs. So if you look at region 1, for the MSTI 0, for IST, same thing, VLANs 21 all the way up to 4096, they're automatically there because VLANs 1 to 10 are in instance 1 and VLANs 11 to 20 are in instance 2. So that means from 21 up, they're just by default non-active and go into that MSTI 0. And it is the only instance where you send and receive those bridge protocol data units. And it creates that loop-free topology for all instances. Then you've got CIST, common spanning tree. It's that link between regions. And it allows that loop-free topology again to be calculated and determined between different regions. And please remember, a region is based on particular comparisons. Specifically, for different regions to not be the same region, the configuration name will be different, or maybe the revision number, or maybe the VLAN to instance mapping, or maybe all of them. If none of those match, they will be in different regions. But that CST is mapping that region 1 to region 2. And from an outsider's perspective, they appear as one logical switch. As I've been calling it, one big giant switch. And thus, to prevent that loop, we need those designated ports, root ports, and alternate ports between different regions. And then there's the CIST, the common and internal spanning tree. It's the combination, it's the addition of all of those ISTs in each region and the CST between regions. And it is for the MSTI 0 only to, again, calculate that loop-free topology between regions. And because of CIST, where we're combining the ISTs in each region and the CSTs connecting regions, you've got to have a root bridge, and that's what the CIST root is. Because each region is viewed as one big logical switch, you need a root bridge. You've got to have the best or lowest cost to get from one region, from one logical giant switch to another region, to another giant logical switch. And that is what the CIST route is doing, is it's providing the best or lowest cost to get from one region to another region. And don't forget that external path cost is only for the CST, the common spanning tree, the link between regions. It's not taken into account the internal cost inside of a region as well. But additionally, each region will have its own regional route. So just because switch 6 was the CIST route doesn't mean it's also going to be the CIST regional route for region 2. I would imagine that pretty much that's always going to be the case, because it's going to be based on priority first. And obviously lower priority wins. So I would imagine the CIST route will also be the regional route for that region. But in each region, you will have a regional route as well. Again, to calculate that loop-free topology. And finally, that master port allows traffic to pass for all VLANs that are not in MSTI 0, that are not in the IST, for all VLANs that are active. So if you have active VLANs, in our illustration, VLANs 1 to 10, they will go through that master port. And also, because of that, you can't have that same switch having another root port, and that is why it's then called the master port. So that's it, everybody. That is the end of this video. That's the end of this part on layer 2 switching. I hope you found that useful. I hope you found that informative. Gone through a lot of information, I know, but MSTP really builds on RSTP. And as I said at the beginning, STP and RSTP, they're VLAN not aware, they don't know, and they don't care about VLANs. MSTP does. And because each VLAN is a broadcast domain, it makes it a bit more complicated and there's more theory to it. You know, with the IST that's running inside a region, and the CST, which is combining regions, and then you've got the CIST, which is really the combination of both of them, and then you've got to have that CIST route, which is that route bridge for the whole domain, and then you've got the regional routes as well. So yeah, MSTP is more complicated, absolutely, but then it gives more benefits, absolutely, to networking for layer 2 networks and for that load balancing, and taking away that burden off of the devices, of those switches, to process all those BPDUs. But again, hope you found that useful, hope you found that informative. If you like my content, please give me a thumbs up. Best way to support my channel. Any questions or comments, let me know down in the comments box. I love hearing from you all. Other than that, thanks for watching and goodbye.